Hello and welcome to this sixth session on symmetry in chemistry, and we're going to be looking at combining symmetry operations and also getting matrices involved, which will turn out to be very useful. And so we're going to start off with our propeller shaped molecule, our trisethylene diamine nickel 2 complex, and this was our D3 symmetry. So this was the symmetry you might remember, which was chiral and where there were only rotations. So there are just 6 symmetry operations altogether. There's the trivial operation E, the do nothing operation. We've obviously got the threefold symmetry going through the center of both of the triangles that you can see, and obviously we can rotate 120 degrees and rotate 240 degrees, so we get 2 operations out of that symmetry element. And there are also 3 C2 axes. So one thing to say about this, because it's D3, D for dihedral, that means that we must have 3 perpendicular C2 axes. So these C2 axes will go through the nickel atom, or the nickel ion if you like, which is between the 2 triangles. So obviously we're looking on top of the upper face triangle. We've got to try and imagine the C2 axes, 3 of them, as it were, between those 2 triangles. And so where we see the 2 triangles on top of each other, at the midpoint between the vertices on the upper and lower triangles, we're going to have the C2 axes. And so we can see there, obviously we've got 6 nitrogens, 6 gaps between them, and so there will be 3 pairs of those opposite gaps where these C2 axes are going to go. And so when it comes to these operations themselves, we take the operations to be anti-clockwise. So on your XY axis, moving from the positive x-axis to the positive y-axis, this is an anti-clockwise direction. We take that to be a positive angle. And so now we'll start looking at combining these symmetry operations. So I ask the question here, what if C3 is followed by C2? And so just for the purposes of this exercise, we'll take the C2 axis to be horizontal, and we'll consider the nitrogen at the very top. So that top nitrogen there on the picture, that's from the triangle that's behind the one that we're looking at. So the C3, so a positive angle there, we'll take that C3 rotation to be anti-clockwise by 120 degrees, and that takes the top nitrogen from the back triangle down to the bottom left side of the back triangle, 120 degrees anti-clockwise rotation. And then after that we're going to do this C2 rotation, the horizontal axis there, going through the nickel atom. So when we do that flip, that takes it up to where the nitrogen was above it. So this is on the top left hand side of the front triangle now. And so what's the net effect then of doing those 2 operations? How did we get the nitrogen from the top position on the back triangle to the top left position on the front triangle? And I think the answer is we must have done a C2 rotation, but around a different C2 axis, the C2 axis that bisects those 2 nitrogen positions. So what we found is that the C3 operation followed by that horizontal C2 operation is equivalent to a different one of the operations in that group, one of the other C2 axes. Now what would happen if we did those operations in reverse order? So again, if we start with the nitrogen atom on the top, supposing we begin by doing the C2 rotation from that horizontal C2 axis, I think that would flip that nitrogen right up to the top, where it's on the top triangle, but the bottom corner of it. So you could flip it up there. Then we do the C3 rotation, anti-clockwise, 120 degrees, and so that would take it around to the top right corner on the front triangle. In other words, it's moved to a different position. Last time it was the top left corner on the front triangle. And so again, combining those 2 operations in the different order, doing the C2 followed by the C3, again that's equivalent to a different operation in the group, and it's yet another C2 axis that it's equivalent to. So it's reinforced this message where the two operations combine to give a different operation in the group, but we also see that doing the two operations in a different order gives a different result. So in other words, we're seeing here that the order of operations matter. That turns out to be very significant. Now, I don't know about you, but I find looking at that sort of propeller-shaped molecule, even if you've got a nice fancy picture to simplify things, it's quite hard work. And there is an easier way of doing it. And what you do is you look at a much simpler picture, like we've got on the screen at the moment, just a regular equilateral triangle. But you could say, hold on a moment, that doesn't have D3 symmetry, because a pure equilateral triangle will actually be D3H, because it's got that plane. It's got a planar symmetry in the plane of the triangle. And that is true. And the other thing I should say, of course, is that not only does it have that plane, but it's also got the planes that are perpendicular to the plane of the triangle. So we've got basically mirror planes all over the place. We've got 3 mirror planes that are coming vertically out, plus we've got the mirror plane, which is in the plane of the triangle. I mean, technically we've got improper axes of rotation as well. So there are a lot of additional symmetry elements, but what we can do to make life easier for ourselves is we just look at the very simple picture, which is the equilateral triangle, and say let's just forget about all the mirror planes and all the improper rotation axes. Let's just focus on the proper rotations, and then actually the whole thing becomes much easier. So there you go, it's really a D3H what we're looking at there, but if we just consider the rotations, then that's a more convenient way of considering D3. Now, just considering our 6 rotations in the D3H point group, what we're going to do is we're going to look at all the possible combinations of doing 2 of these symmetry operations. And so we're going to draw up a 6x6 table doing each operation followed by each other operation, all 36 combinations. And then how do we label the C2 axes? So, I mean, there are lots of things you could do. I'm going for a system here kind of using the points of the compass. So the C2 axis I'm calling north is just going to point straight up, so it's going to bisect the triangle going through vertex 1. And the ones that go through vertex 2 and vertex 3, I'm calling them southwest and southeast. They're kind of pointing down in that direction, going towards corners 2 and 3. And the reason I've done points of the compass is I didn't want to use the numbers actually, because as for example you rotate the triangle around, obviously the numbers are going to be moving, but I wanted just to keep the C2 axes just in the same place the whole time, so they're kind of relative to the page rather than any movements we do on the triangle. Now let's combine the 6 operations of the group with another one of these operations and see what we get. So here is our 6x6 table. So let's just have a look at this table. We've got these 6 rows, each are labelled by one of the 6 operations. Likewise, the 6 columns are each labelled by one of the 6 operations. The do nothing, the 120 and the 240 degree rotations around the threefold axis, and then there's the 3 C2 axes in there as well. One thing that will strike you straight away, because I've colour coded it, is you can see that we've got a row and a column in green there. And what's special about the green one is that in all these cases the operation E, the identity, is involved. So clearly if there are 2 operations and one of them is the identity, the net result is just going to be the other operation, as the identity is just to do nothing. Then otherwise we've got these 4 corners in the table. Perhaps I should make clear that the operation in each cell is the result of doing the row label followed by the column label, so doing them in that order. If we look at the different quarters there, the bottom right hand quarter is quite interesting, because in this quarter here it's a C2 rotation followed by another C2 rotation, and you can see down the leading diagonal we've got the identities, and that's because we're following a C2 operation by the identical C2 operation. So it's a 180 degree rotation around an axis followed by another 180-degree rotation around the same axis. So it's a 360-degree rotation around that axis, which is the same as doing nothing, which is why we get the identity. But if we've got C2 rotations around different C2 axes, then when you put them both together, there's going to be a C3 rotation operation. And in this case, you can see that the order does matter. So you can see, looking, sort of reflecting through the leading diagonal on that bottom right quarter, we can see there we've got different results. Then looking at the bottom left and the top right quarters, these all involve a C2 operation and a C3, and we can see that the product of these is a C2 operation. And we're just asked here to look at about patterns and symmetries in the table. Quite interesting in the top left hand quarter there, and so you can see here, we'll return to this, that just looking at the threefold rotations and the identity, all the elements in that little box are themselves threefold rotations or the identity, and we'll look at that significance of that in the next slide. So going back to this 6x6 table, we can look at it in a bit more detail, and we see some interesting things drop out of this. So you see that if you look down any row, any of the 6 rows in that table, you'll see every operation appears once and only once in each row. And curiously, when you look down each column, every operation appears once and only once. It's a bit like doing Sudoku, isn't it? And then, going back to this top left-hand corner now, what we find is that's like a little self-contained group, because we've got the E identity and the 2 types of threefold rotation, and all the combinations of these things all result in that same group of operations. So it's like a little self-contained group, and in fact that is actually a subgroup of D3, which is C3. So it's nothing more than the threefold rotations. Of course, not being a D, not being dihedral, you haven't got all the C2 perpendicular axes. And rather like we saw before with the descent of symmetry, we see here that the number of the order of this group, if you like, which is the number of operations, is 3, and 3 here is a factor of the order of the parent group, the D3 group, which was 6. So this was consistent with what we saw about descending symmetries in groups. Now, commutativity, interestingly, so we mentioned about this. This is to do with the order in which you multiply things together. And while there were a small number of cases where the order didn't matter, we can say that in general we're going to have to assume that the order does matter. We certainly can't assume in this case that we can do the order any way we like. And so if the order doesn't matter, we call it commutativity or commutative. And in fact, there's a nice little comparison here with, say, addition and multiplication. So obviously 2 plus 3 is the same as 3 plus 2. Addition is commutative. 2 times 3 is the same as 3 times 2. Multiplication is obviously commutative, but it doesn't work out that way with subtraction. Obviously 2 minus 3 is not the same as 3 minus 2, and the same as 2 divided by 3 and 3 divided by 2. So this is where we might consider commutativity regularly, but we also, crucially, it's an issue when it comes to combining symmetry operations. So in the overall parent group, D3, the sort of 6x6 table, we can't generally assume that everything's going to commute. But one thing that is quite interesting is that when we look at this C3 group here, that's just the top left-hand quarter, these things are commutative. So when you look at, so we've got that leading diagonal, and then when you look at things that reflect across that diagonal, these are doing the operations in different order. And so in the particular case of C3, the operations do commute. And then I make the point here that in fact all cyclic groups commute. And why should this be? Well, I suppose if all you can do in a cyclic group is rotate around one axis, then in a way it's just a bit like addition, isn't it? So you're doing one rotation, that'll just be like an angle around that axis, followed by another rotation, that's just another angle on the same around the same axis. So really you're just combining these angles just like addition. So cyclic groups commute because essentially there's just one axis and all you're doing is rotating around it, and all these angles will just be adding. So I'll make the point here, in terms of things commuting, D2H is quite a significant point group because it's the highest symmetry group where all the operations commute. So you notice that in this case there's no rotation of order greater than 2. So I think once you've got a rotation of order greater than 2, then having the presence of mirrors in the molecule will stop commutativity happening. So your D2H there, fairly significant, high symmetry commuting group, and abelian is the technical term that you give to one of these groups where all the operations commute. Now, looking at groups in more detail, and so the relationships that we see in a table like this between the different symmetry operations, if you repeat them, these actually reflect a so-called group structure. And what's great about this is it's totally abstract. I mean, in this context, we're looking at symmetry operations, but in a way it could be anything. It's just the combination of things and their result. And so this can also be applied in a very general sense with the most simple things like, just permuting objects. In a way, symmetry operations kind of are just permuting objects, aren't they? We're just like permuting, for example, the corners on a triangle. So what properties do we see from this table? So we list some of them here. And that is that of these group operations that we see, of these symmetry operations that we see in a group, one of them has to be the identity. And this is just an absolutely prerequisite for all the group operations to follow this kind of standard set of rules which allow us to call them a group, which then lead on to so many other important things that we're going to discover. So we need the identity. Another thing that we need, that we were commenting on earlier, is that the product of any two operations of the group is another operation of the group. So again, this applies in the most abstract sense. So here I'm talking about symmetry operations, but whatever abstract thing it is that you've got, the objects that you're making into a group, the product of any two of them is another one of those members of that group, or symmetry operations in this case. And this is an interesting one. For every operation in a group, there is an inverse operation. And so that's a bit like saying, for any operation in a group, there's something you can multiply it by, and the result is the identity. And if you think about it, that kind of has to be true, doesn't it? Because do you remember in our multiplication table, you had to have every single operation somewhere in every row. So you have to get the identity somewhere in every row. And if the identity is somewhere in a row, that means that your operation, which is your row identifier, has to be multiplied by another operation to give you the identity, or the identity wouldn't appear in the row. So there we go. And our final one here is to do with associativity. So while we don't normally see commutativity in groups, only in the abelian groups, we do generally see associativity. So you can see here this little equation. So A, B and C, they're always multiplied in the same order, but you can combine them separately, if you see what I mean. So in this case, going from right to left, you'd have C multiplied by B, and then the result of that is multiplied by A, as opposed to, if you like, B multiplied by A, and then C multiplied by the product of that. In both cases, you'll get the same. Now we're going to be looking at symmetry operations in the form of matrices. And this turns out to be very profitable indeed. And in fact, just as we've been combining symmetry operations, we can combine matrices in the same kind of a way, and it's going to be very useful. And of course, you know, don't you, that matrix multiplication isn't necessarily commutative, just in the same way that we found that combinations of symmetry operations aren't necessarily commutative. So actually, introducing matrices is going to actually open up whole new dimensions for us, and it's going to be even more powerful than we thought. And so what we want to be able to do is to take a symmetry operation and represent it as a matrix, and we're going to see how to do that here. So let's look at the general case of a rotation matrix. So on the graph here, I've got some point which I've labelled x1, y1. And what we'd like to do is apply some matrix that will represent a rotation by the angle theta, and hopefully then if we get that matrix, make it act on points x1, y1, it should generate points x2, y2. And so really the trick to doing this is, rather than just considering like a single sort of vector taking you straight to x1, y1, we consider it as the sum of the two perpendicular vectors, the vector x1 going along the x-axis to the point where it's labelled x1, then the vector y1 going up the y-axis to the point where it's labelled y1, then we sum them together, and then together that gives us the point x1, y1. And so we're going to do the rotation of theta separately on these two perpendicular vectors. And so that x1 vector, when you rotate that by theta degrees, then there'll be a component of that still on the x-axis, that'll be x1 cos theta. When we take the vertical y1 vector and rotate that by theta degrees, that will introduce a component onto the x-axis, but actually because we're rotating anti-clockwise, starting from the vertical, it's going to rotate it onto the minus x-axis. So it's actually going to give us minus sine theta as the component on the x-axis. And if we add these components together, that should give us the x component on the resultant point, that's to say the point x2. And we're going to do the same thing as well with the y. So for example, if we rotate by theta degrees the horizontal vector x1, obviously that now rotates a component into the y direction, and so this now, so that is going to be that's going to be x1 sine theta, and similarly the y direction there, the y-axis, when we rotate that by theta, that's going to put a component onto the y-axis as well, and that's going to be the y1 cos theta. And so they should sum up to give you the y2 there. And so having done these, using a bit of trig to do these rotations by angle theta on the component x1, y1 perpendicular vectors, we should ultimately sum these up and we express the result in the form of a matrix equation there. So there you go. So as I was saying before, the x1 times cos theta minus the y1 times sine theta, that gives us the x2 coordinate, and the x1 times sine theta and the y1 times cos theta, if you add these together, they'll give you the y coordinate. And that's all encapsulated in this very neat little matrix. So that's a very convenient way of holding the information for our symmetry operation. So now we're going to go from the general case of rotation by theta to a much more specific example. So as you can see in the picture here, we've got some threefold symmetry. So we see this triangle, and what we're going to do is we're going to do a C3 rotation, and this is going to operate on our point on the right hand side, the 1, 0 coordinate, and it's going to take it up to -1/2 √3/2. So what we do is we take our general rotation by theta matrix, and all we'll be doing is replacing theta by 120 degrees. And since the coordinate we're acting on is 1, 0, this is going to be very quick and simple. One of our coordinates is 0 anyway. So you can see here, all we need to do really is think about the operations on the x coordinate. So you can see that we're going to have cos of 120, therefore, which is the -1/2. That's going to be the new x coordinate, and then looking at the second row, the sine of 120, that's your root 3 over 2. That's going to be the y coordinate. So that's shown how we've done this threefold rotation to rotate 1, 0 to minus a half root 3 over 2. And so you see, in this particular case, we're just looking at a plane, so we've only got the x and y axes here. But if you wanted to generalize this to three-dimensional space, then clearly a rotation around the z-axis isn't going to affect any z-coordinates. And so this is manifest in a 3 by 3 matrix, just in the third row and the third column, you're just having that extra 1 in the corner there. And then this just leaves you going from 1, 0, 0 to having a 0 in your new z-coordinate. Right, and so now what we can see is that when we've been combining symmetry operations, we can do the same thing with matrices. So for example, if we want to do the C3 operator twice, we can think of it as by squaring the C3 matrix. And so here we've got the C3 matrix multiplied by itself. Now at the moment I've just got it in the general form, so I've not got theta as 120, but just putting in the general form of theta there. And what I've just simply done is I've taken the 2 by 2 matrix, I've squared it, I've just multiplied it by itself. And so what we're on the right hand side there is the product. But significantly, if you apply the trigonometric identities, if you look at those expressions, they're all double angle formulae. So in fact, the other way of writing the matrix we see there. And of course, what we see now, this just resembles the original matrix, except the angle's been doubled. So this illustrates to us that when you do a rotation operator twice, it's just the equivalent of the original matrix, but with the angle doubled. So it's just common sense, really, I suppose. So that's the fairly obvious result. And so this shows again how these matrices are very amenable to showing combinations of operations. There you go. So this has proved to us that, if you like, C3 followed by C3 is this C3 twice. Now we can look at mirror plane operations. So for example, you can see in the diagram here we've got the x and y axes in red, and we've got a couple of mirror planes. We've got an x equals y mirror plane there labelled black line, and also an x equals minus y mirror plane. So for example, if you were going to reflect in the x equals y mirror plane, as it reflects across that mirror, what you're effectively doing is exchanging the x and the y coordinates. And you can see that the ones in that 3 by 3 matrix, the ones you can see in positions 2, 1 and 1, 2, those are going to invert the x and the y, so they become y and x. And similarly, when you look at the third row and the third column, we just have that 1 there on the diagonal to reflect the fact that the z coordinates are going to be unaffected by this mirror. And so it serves to reason then that if you've got a mirror, if you apply a mirror operation twice, it will just go back to where it started. You just reflect in the mirror and then reflect back again. And so you see this matrix there, if you multiply it by itself, it just generates the identity. And so you can see that if you've got a matrix that's all zeros, apart from 1 down the leading diagonal, that is simply going to take x, y, z and convert it to x, y, z. In other words, it's the identity operation. It's not going to move any points. Now this is an interesting one, the improper rotation. So you can see in the picture here, and this is going to be an S4 axis, and so you see what looks like a methane molecule there, and the C4 rotation there around the axis of interest. So what's slightly confusing about this is that actually this will be our z-axis, the improper rotation axis will be the z-axis. So we rotate around that axis. So for example, D there will move up to the vertical, A will now move around sort of to the horizontal and towards us. And then once we've done that rotation, we then reflect in the perpendicular plane with the central atom in it. And so you see the D and the C there, which are on the left-hand side of the plane, they reflect across to the right-hand side, and the A and the B reflect back to the left-hand side. And now the molecule has the same orientation that it did at the start, but we've just permuted the equivalent atoms A, B, C, and D. And so when we look at this in matrix form, the C4 rotation there, this just looks like the sort of 2 by 2 matrix in the top left, the cos theta, the sine theta, and the minus sine theta. Remembering, and then we've got the z-axis in there as well, and this is what the -1 represents in the bottom right there. So this reflects the fact, because of course in the z direction, if you're on the actual z component isn't going to be affected by the rotation, because it's rotating around the z-axis, but then when it comes to the reflection in the mirror, the z is beginning to become minus z. So you can see obviously in that horizontal axis there, if we have 0 where the central atom is, everything goes to minus that distance on that axis. What's interesting about this is that when you apply the improper rotation twice, you then have to square that matrix. And so we see that using the same process as before and the double angle formulae, all the angles come out doubled, but now the -1 has turned into 1. Obviously when you square -1 you get +1. And so when you do the improper operation twice, you actually end up with a proper rotation, reflecting by the fact you've got +1 in the bottom right there. And that's one of the things that's one of the features of improper rotations. When you do 2 of them, it turns into a regular rotation. So essentially if you do an even number of improper rotations, they look like proper rotations. And finally we've got center inversion. So each point's going to reflect through the center of symmetry and come out the other side. And so essentially all the coordinates get reversed into their minus coordinate. So x, y, z is turning to -x, -y, -z. And so it's rather like the identity matrix here, except rather than x, y, z turning to x, y, z, it's -1 on the leading diagonal. So they all turn into minus themselves. And so, of course, this center inversion matrix, this is the same as an S2 axis, isn't it? So actually this is what you get in terms of our general rotation matrix, if you've got, or our general improper rotation matrix, if you have theta equal to 180. So you get these numbers dropping out. And of course, not surprisingly, if you take this S2 center inversion matrix, if you do it twice, reflecting through the center twice, you go from xyz to -xyz, and then you just change the signs again, and you go back to xyz. And so not surprisingly then, when you multiply this matrix by itself, you get the identity, because of course you're only on the leading diagonal, and -1 times -1 is +1. And so finally, looking at inverse matrices, and these are quite interesting. One nice way of looking at this is the fact that every single symmetry operation you do actually boils down to either a proper rotation or an improper rotation. So remember, we can talk about mirror reflections effectively being improper rotations of order 1. We've got center inversion symmetry as improper rotation order 2. We can even think of the identity as like a C1 rotation. So we can look at all these things in terms of rotations of one form or another. And so if you think of every single kind of operation as some kind of rotation by angle theta, then it follows that the inverse matrix would be the same thing except over an angle minus theta. Clearly minus theta will just undo theta. And so clearly if you're going to do an inverse operation, it's going to be in the same class, it's going to be the same type of operation, just the angle will change. And so what we see here is we've got a general improper rotation here, and what we've done is we've changed theta here for minus theta. But the curious thing is that cos of minus theta is the same as cos of theta, whereas of course sine of minus theta is the same as minus sine theta. So when you take that into account, you see that the inverse operation here actually takes this form on the right hand side with the cos theta, sine theta and minus sine theta. And what you notice about this, when you compare this to the general rotation matrix, or the general improper rotation matrix rather, you find that what you've effectively done is you've reflected in the Lie diagonal, because the sine theta and the minus sine theta have changed places. And in fact it's a general result here that the inverse matrix of any of these symmetry operations is the transpose of the original matrix. And so essentially you're just reflecting all of the elements in the leading diagonal, and that's the same thing as just switching rows for columns, which is something you can do in the square matrices. Obviously they still stay a square matrix. So there you go, you transpose the rows for columns and then you end up with the inverse matrix, following this logic here, following on from these trig rules. So there you go, that should hopefully give you some insight now into how matrices can represent symmetry operations and how we can get information about combinations of symmetry operations by multiplying together the matrices, and how you get some quite neat results from the multiple angle formulae.